Hi everyone. Now we are going to take a walkthrough of our code base and what we have done for the project. And first, let me walk through the project structure. And this is the project structure where we have data here, and the data comes with a already split in data with the test, train, and validation. And we have three classes for each split. And here, this folder is to save the models, the model and the history of the model. And in this folder, we are going to actually save the model. For each model, we have created a separate Python file. And we also have the common files like exploratory data analysis file and the utils file, where we are gonna use these functions uh, throughout the project. And in this EDA, we only have the code for data analysis. And let me go through the final project where I have implemented all the code in a single go. And first, I am setting the data path here, and this is the results for the complete exploratory data analysis. And first, we check the paths and we check the classes whether they are correctly aligned or not. And we created the data frame, and we check the class balances. And if you see, the class is already balanced, and we see whether the images are RGB or not, and we see the corrupted files and all. And then we see the file distribution, I mean the size distribution of each file. If you see, it was spread across the plot, and like few images are very high size and few images are very small in size. So we did some pre-processing and augmentation techniques before creating the model. And and this is the brightness check for the all three classes. If you see, the rust is like very bright when compared to other two classes. Similarly, when we check the RGB channel values, the two healthy and the powdery classes are very similar and overlapping. And this is actual data set, like before pre-processing. This is how actually our images look like. If you see, the images are blurry. I mean, like the background is very blurry, and even that is also in green. So sometimes the model fail to capture the main images and capture the noise instead. If you see the other images, there are this is the biggest challenge come from the data set. This all looks good from the data set point of view. And let's go through how we build the model. And this is the baseline model. We have first chosen with 128 resolution. Here is the code for that. And this is a simple architecture with the three layers and the activation relay. And we also have the callbacks for this, and the epochs and everything was set inside this Python code. And also, if we run this baseline here, it will automatically save the model to avoid the retraining again. The model will save, and the metrics, the history of all the epochs and the metadata of the model, like the hyperparameters and the learning rates, epochs, and the callbacks and everything was stored here. And obviously the curves and all. So this is mainly to avoid the retraining for all the models. And coming to the results of the baseline CNN. If you see the results, the test accuracy is 94%. And if you see the confusion matrix, mainly the misclassification is happening between the healthy and the powdery. The phi uh, is like the between these two classes, and rest all look good, and only these two classes are confusing. So let's see how this to 24 resolution baseline work. And if you see, the model is very similar to the baseline model, and the results also like look very similar. And I got 92. The test accuracies are a bit different because we have very small test set like 150. Even in one or two image, misclassification lead to drop in the uh, test accuracies. But overall, if you see the curves, the model looks good, similar to the 128 resolution model. And when we come to the improved CNN model, here is the code for improved CNN model. This is the hyperparameters and the callbacks we have set for this model. And here we increase the model with one more layer, and also we choose the batch normalization and all. And we make sure we this time we use the longer epochs with a careful uh, learning rates. Uh, and let's see the output of the model. If you see the curves, it was very close and almost converge. And also the test accuracy is 94, very similar to the baseline. But maybe when we test with the real world data, it may perform better because when I see the curves, it looks good. So even now the confusion matrix is struggling, the classification is struggling with the two classes. Let's see whether the pre-trained models can do better or not. I just go through the pre-trained models. Even the pre-trained models follow the same structure of the code. Like we have code for each pre-trained model for the fine-tune and the normal pre-trained model. We choose the transfer learning techniques because given the data set is very small, and uh, it was very challenging for the CNN itself to capture all the patterns. So that's why we choose the pre-trained models here. It might be better for the problem we are solving. And coming to the efficient net B0, these are the curves. And also while implementing these pre-trained and transfer learning models, we make sure the code is using the proper learning rates and the proper callbacks and the patience and all, like because the main thing is to avoid the overfitting. That's why we choose the slow learning rates here. Even in fine tuning, if you see the results, like it was improved. Like even without fine tuning, efficient net can reach 97. So let's see like how fine tuned efficient net will perform. And the scale is different, but if you see the graphs look very converging and very close to each other. And even though fine tune not performed outperform the efficient net pre-trained model, but it is very equal to the pre-trained model. So in this case, in this particular pre-trained model, the fine tuning is not improving the model accuracy. Let's see like how other models will perform. And throughout the project structure, we design like retrain is equals to a parameter, because if we set the false, we can directly reload the uh, already uh, existing models, so to avoid the retraining and all. So Harika will continue with the other pre-training models.
Yeah. So next we have VGG 16 model. And first we go with the pre-trained VGG and then we fine tune it. It has 16 layers 16 layers in its architecture, and it has 3 by 3 convolution layers. Yeah, so this is the .py file for we have for the pre-trained VGG. And then going back to the final project, the IPYNB file. After we actually used 2 stages to train the model, and coming to the results of the pre-trained VGG, we achieved 96% in test accuracy. Yeah, it says 96%. And coming to the actual confusion matrix, we can see that it performed better compared to the previous models. We see it only did bad in 2 scenarios, and it did pretty well in to classify healthy, poultry, and rust as well. Coming to next fine-tuned VGG model. So we yeah, this is the .py file of the fine-tuned VGG 16 model. And Yeah, here comes the fine-tuned VGG model results. We can see that now and then in the plots, the model did have some overfitting issues, and it did converge pretty early. Coming coming to the accuracy, we can see that we achieved 98% accuracy, but while running, we did see that computationally it was very heavy and it took us the longest time to run actually. So even though it did give us 98%, it is computationally very heavy. And coming to the confusion matrix, again, we can see that it is almost similar to what we saw in the pre-trained VGG as well. So again, it had just very few confusions between healthy and powdery, but other than that, it did pretty well. And the last model we used is ResNet. So this is a .py file of the pre-trained ResNet 50 model, and yeah, coming to the pre-trend, we can see again it did converge pretty well, but now and then it had jumps, but it achieved a very good accuracy of 94.67. And then in the confusion matrix, we can see that it performed almost similar to the VGG 16 model, where it had some confusion classifying again between healthy and powdery, but the other scenarios it did pretty well. Now coming to the very last fine-tuned ResNet 50. So we again have two stages here, and then we see the results that it converged pretty fast again, smooth validation as well. And here we achieved the best accuracy, which is 98% with very less test loss of 0.06. So if we look at the overall results, CNN did perform well, but compared to the pre-trained models, it did not perform as well as the pre-trained. So over CNN, the pre-trained models are better. And compared to the three pre-trained models we use, which are EfficientNet B0, VGG16, and ResNet 50, if we want to go with the model that gives good accuracy and good efficiency, we can go with the EfficientNet B0, as it performed well both in pre-trained and fine-tuned. If we want to get the good accuracy, we can go with ResNet 50 fine-tuned, as it gave us 98% accuracy and very less test loss. And VGG 16 also performed well, but compared to these two models, that was computationally very heavy. So this was our project of classifying leaves between healthy, powdery, and rust, and we used CNN. Uh, from a custom CNN, and we use three pre-trained models. This is our code demo. Thank you.
Thank you so much.